Just before we start, could please everyone expect me and the speaker turn off the microphones? Thank you. Okay, I think we are free to start. So welcome to the Crowdsourcing seminar. These seminars cover a broad area of human-AI collaboration to allow discussing past and future work, exchanging ideas, and establishing new collaborations. Today we have a talk by Ivan Stelmakh on the principal design of human decision-making systems. In such systems as crowdsourcing, peer review, employee performance review, etc., how can we actually handle noise, strategic behavior, and various kinds of bias? I hope we get useful insights today. Ivan is a PhD candidate at Carnegie Mellon University. His research is focused on human AI collaboration, and he has already published works at NeurIPS, AIII, and CSCW. Ivan served as a workflow chair of the ICML 2020 conference, and he is also an editor of the Machine Learning at Carnegie Mellon University blog. So it's a great honor to have him today. Now I'm giving the stage to the speaker.
Thank you, Dima, and thanks everyone for coming to this talk. So today I'm talking about a general area of human decision making, and the talk is partially based on my works with my advisors, Nihar Shah and Arti Singh, but we'll cover some other works as well. Okay, so to begin with, let's try to parse the title. So what do we mean by decision-making systems, and why do we need the principal design? So let's start from the decision-making systems. And yeah, in previous editions of this seminar, we've been mostly talking about crowdsourcing, so people may be familiar. But for those who are coming for the first time now, let me quickly recap what do I mean by crowdsourcing. And when I talk about crowdsourcing, I generally refer to crowdsourcing platforms like Toloka or Amazon MTurk. So these platforms maintain a crowd of performers. So if you have some task, for example, you want to label a data set of 1,000 images, then you can put up your task to the platforms, and performers will work on your task for some compensation. As a result, you get labeled data. And this is kind of an example of the human decision-making systems, because there are many people working side by side to solve some complex tasks. And beyond crowdsourcing, there are a bunch of other examples. For example, companies do performance review to understand how their employees perform throughout the year. And this is also an example of human decision-making systems, because this review are often based on evaluations made by employees. So employees rate each other, and these evaluations are then aggregated into final score of each employee. And this is very important because bonuses and promotions are distributed through the system. And other examples are academic peer review. So each publication, each scientific publication goes through the system in which it is read and approved by several researchers working in the same area. And in academia, peer review serves like as a validator of scientific rigor of publication. And finally, in education, it's now become common practice to rely on peer grading. So students grade each other's homeworks, and this saves a lot of work for instructors. And this technique is very often employed by Coursera and other platforms. So in this talk, we'll focus on these kind of systems and what, they seem pretty different, but what unites them is that in this system, we try to learn from people. So in each application, there are a bunch of people, and we want to learn some valuable insights from them. All right, so that's it about systems. But now let's think, why do we need a principal design? And to this end, let me quote a paragraph from a Nature article. And in this paragraph, so Drummond Rennie talks about one application, which I mentioned in the previous slide. So he says that this application is a human system, and hence everyone involved in the system brings prejudices, misunderstandings, gaps in knowledge. So we shouldn't be surprised that this application is biased and inefficient. I mean, you can take a guess of what application he means. Maybe someone wants to make it publicly. But yeah, let me tell you what is the application that Drummond Rennie is talking about in this paragraph. And it may be surprising, but this application is an academic peer review. So the system which lies at the heart of academia and which is responsible for dissemination of rigorous scientific results is itself not scientific. And this sounds pretty surprising to me, and maybe it sounds surprising to you. And if peer review is not scientific, that what can it tell about other applications like performance review in companies or peer grading or even crowdsourcing? So how scientific are they? And this question kind of brings to their direction of my research. So in my research, I worked on making the design of the systems to be principled. In this, I designed various algorithms, tools, and techniques to address systematic problems which arise in large systems where human makes decisions. Okay, so in this talk, I'll give 3 examples. So we will go through 3 cases. First, we will start from strategic behavior of agents. Then we'll continue to noise, and we'll conclude with a small remark on biases. So I'm happy to answer any questions as we go. So please don't hesitate to interrupt me and ask your questions, or you can, type them in chat, and I guess Dima will give them to me when he finds it appropriate. And yeah, in this talk, I'll try to avoid technical details, and instead I'll try to focus on some general intuitions that are applicable to wide range of applications and which you may find interesting. So let's begin from strategic behavior, and yeah, let's see what it is. As I have said, in the human decision-making systems, there are many people who work side by side to solve some common goal. Like in crowdsourcing, we want to collect high quality data. So we submit a data set and we expect to get high quality data from performers. But on crowdsourcing platforms, there are people who come there to earn money. So a strategic performer, a strategic worker may want to earn more money. And the goal of earning more money is not always aligned with the goal of getting high quality data. In fact, a strategic performer can spam, and return use some script or give some wrong random answers to just do your task fast and get some money. And this is where misalignment of incentives comes into play. So our incentive and our goal is to get high quality data. However, performers are not necessarily interested in this goal, and they may have some other goals. And this is where strategic behavior begins. Another example is peer review. So in peer review, there are in academia, there are many conferences, and these conferences receive thousands of submissions and want to accept some of them for publication. And typically they want to find good papers for acceptance. And reviewers who serve in peer review often themselves submit papers to the same conference. So while conference organizers want to find top papers, each reviewer may be interested in getting their paper accepted. Hence, a strategic reviewer is incentivized to manipulate their evaluations of others to increase chances of their own paper. Finally, if you talk about performance review in the companies, then again, a company wants to get a precise estimate of performance of each employee. However, each employee wants to be evaluated, wants to be seen in a good light. So they want to get promoted, they want to get bonuses. So strategic employees can again manipulate their evaluations of others to end up higher, to get more bonuses. So these are 3 examples in which strategic behavior, hurts us and does not let us to reach the overall goal of the system. So what can we do about this? How do we avoid strategic behavior? And the most popular approach, and the reasonable approach, is to design a system such that incentives of performers and employees and reviewers are aligned with the incentives and goals of organizers. So to give you an example, in crowdsourcing, we can connect payment of a performer to the quality of work done by the performer. So we can use some golden set questions, the questions that we know are the correct answers, and we can see how well the performer performs on these questions and connect their payment to the quality of the performer. And in other applications like peer review and company performance review, there are complex solutions designed which probably help you to alleviate strategic behavior. However, it is unfortunately often the case that despite there are solutions and which prevent strategic behavior, in real life they are not implemented. And for example, if you submit a paper to a conference like NeurIPS and ICML, then there are essentially no measures are taken against strategic behavior. So why does this happen? And one problem is that to implement the solutions into practice, there is a significant threshold for this implementation. And a lot of logistical burden arises and organizers just don't have time to implement this. And second, so when there is no strategic behavior, so when all agents involved in your system are truthful, their solution that is targeted against strategic behavior may actually hurt you. Because it gives you some guarantees against strategic behavior, it limits your power when there is no strategic behavior. So system designers are kind of hesitant to switch to this to these more complex solutions, because they don't know actually if there is strategic behavior in their system. Like, you don't know if in your company employees are engaged in manipulations, or maybe they're just truthful and never engaged in manipulations. So why do you need to protect from it? And this is what brings to my approach to this problem. So in my research, I try to design a tool to detect the presence of strategic behavior in the system. So why this tool is useful? Well, like, the organizer can take this tool, apply it to their data, and see if there is a significant presence of strategic behavior in their company, whatever conference or any other application. And once you have like strong evidence of strategic behavior that actually hurts you, then you are much more eager to implement principled solutions against this. And let me now give you one example of how this can be done. So how can we test for strategic behavior in large systems?
Can I ask one question?
Yep,
For the
sure.
previous slide? So I'm just curious about the alignment of the incentives. And what if you design the system in such a way that you don't provide any incentives to those who, for example, submit reviews? So for example, you ban people to submit papers if they are reviewers. So you exclude them from this potential conflict of interest part. And can it help the problem?
Yeah, I guess if you prevent people from submitting, people who review to submit to your conference, then yes, those who remain, they kind of don't have their stakes, and you may hope that they will review truthfully. So there are kind of two challenges. First of all, do this in a company, for example, because if you prevent everyone from participate in evaluations, then you will have no evaluations, right? Second, even in the conferences, like big conferences as NeurIPS and ICML, they need thousands of reviewers, and there's a huge demand for reviewers, and there are not enough reviewers. So it's like it's not practical to remove some of them and to prevent some of them from submitting. And yeah, but there is also another caveat that even if you don't submit, your friend may submit something, and you will still be engaged in some strategic behavior just to help your friend. But this actually goes beyond, like, this is typically assumed not to be the case, because otherwise it's very hard to prevent such kind of manipulations when you have no idea of what is the interest of the agent. But now let's see the system in which no measure against strategic behavior is taken, and let's see if we can look at the data, at the evaluations, and find whether there was a significant presence of strategic behavior or not. And to this end, let us fix the pipeline. So how peer assessment goes. So we have a bunch of agents, and assume we want to evaluate their performance in the past couple of months or half a year. One option is to recruit some independent evaluators and ask them to evaluate each agent. But this is typically not done, and instead the task is distributed across agents. So everyone rates a subset of their colleagues, and then these evaluations are aggregated, and we get the final ranking of employees. In the system, a strategic reviewer can manipulate their assessment to improve their final position. And that is what we want to detect. So our goal is to design a statistical test to detect a significant presence of strategic behavior in the system. Okay, but let's see what does it mean to manipulate it? How can a reviewer help themselves to manipulate the evaluations of others? So note that here, nobody rates themselves. So the only way you can help yourself is by strategically rating others. And to this end, let's start from score-based setting. So in this setting, you are assigned to evaluate a couple of colleagues, and what you need to do is to give a score to each of them. And if you think a little bit, it's kind of not hard to see that the dominant strategy here is to just give the 0 score to everyone you're reviewing. Yeah, you heard them a lot, and if they were higher than you, then maybe your score will help you. If you give them 0, maybe it will help you, and you will get higher in the final ranking. So this is a dominant strategy in the score-based setting. And as you see, this strategy is not hard to detect in the test. So why? Well, because if a reviewer gives a 0 score to everyone, then it's very easy to notice even at the level of the reviewer, because you see, hey, some of your employees give score 0 to everyone, so something is going wrong here. And that's true. Like I guess in real life, people would not engage in such blatant manipulations, and instead they would try to manipulate but hide it such that it is not easy to detect that this reviewer is engaged in manipulations. And indeed, there's some evidence. So recently, there was a paper by Huang and others who analyzed the data set from some Chinese private company. And in this company, performance review is based on this peer assessment pipeline. So they don't rigorously test for manipulations, but what they suggest is that people may decrease scores of some colleagues, but instead increase scores of other colleagues, such that, on average, there is no change in the distribution of scores given by this reviewer. And these manipulations are now much harder to detect, right? Because it's not like blatant, and you don't see the changes in the mean or variance of scores, but instead still something bad is happening behind the scoring. And this observation brings us to the ranking-based setting. So in this setting, you don't score your colleagues or items you review. Instead, you need to rank them. So if you assign, say, 3 colleagues to evaluate, then you rank them and tell, hey, this colleague is the best, this is the second best, and this is the third best. In this case, and see, this kind of ranking-based setting captures the intuition we considered in the previous slide. So people cannot just give 0 score to everyone. Instead, they need to be much more careful. But this now in this setting, it's much harder to manipulate, right? Because there is no obvious dominant strategy, and it's unclear how to help yourself by strategically ranking others. And obviously, this case is also much harder for detection, because we don't know what is the best strategies for people. So we kind of have to detect something, but we don't know how it should manifest. So let's see. And to understand how we are going to test, let's think about what can you even do to help yourself by manipulating the ranking of others. And let's start from a toy problem. So assume that we are a strategic reviewer, and we are given to rank 3 of our colleagues. So yeah, here I write papers, but yeah, let's just continue with the performance evaluation. So assume we're given 3 of our colleagues, and we need to rank them. Is better than green, and then is better than orange. But how should we rank them to help ourselves? And the first idea that comes, at least to my mind, is to just reverse the ordering. So you put the weakest performer to the first place and the strongest performer to the last place. Let's now think if this strategy actually helps us. Can we help ourselves by just reversing the ground truth ordering of our colleagues? And to understand that it is not always helpful, let's for a moment assume that all of our colleagues who are in the system are truthful. So we are the only one who are engaged in any manipulations. And under this assumption, let's consider 2 hypothetical scenarios. In the first scenario, the ground truth ordering is such that we are indeed the best employee among those we need to rate. So we are better than any of them. And now let's see if reversing helps us. By reversing the ground truth ordering, we hurt our closest competitor. So the blue, who is the closest in the true ordering, gets the last place, and hence we kind of, prevent ourselves from being overtaken by the blue reviewer. Yeah, of course, we promote an orange colleague, so we give them a little bit more that they deserve. But this is fine because others are truthful, and the orange guy anyways won't get too much from others. So here we hurt our competitor, help someone else, but we don't really care about someone else because they are anyways won't get high scores or get high in the rankings of others. So in this case, the reversing may be helpful. But let's consider another scenario. In this scenario, we are in fact weaker than everyone we have to rank. In this case, if we reverse the ground truth ranking, we actually help our closest competitor. So from these 4, we can hope to overcome the orange colleague maybe. But if we reverse the true ordering, then we actually help them and we give them the first place. So it becomes impossible that we will overcome them eventually. And intuitively, if we are indeed weaker than all others who are assigned for review, then reversing actually hurts us. And overall, reversing may be sometimes helpful, may sometimes hurt us. So just simply reversing the ground truth ordering doesn't seem to be a good strategy. Okay, let's see what we can do. And I guess previous example kind of suggests that sometimes reversing helps, but sometimes not. So maybe we should be adaptive and choose our strategy depending on how we compare to people we rank. And this, yes, this may work. So for example, as we considered, if the true ordering is such that we are indeed better than everyone else, then we can reverse. And yeah, it's a good idea. And if the true ordering is reverse, like if we are weaker than everyone who we need to review, then our closest competitor is orange reviewer, and we definitely don't want to promote them. So in this case, it seems that being truthful is fine, right? Because we place our closest competitor to the last place. And yeah, this is kind of the best we can do. We cannot hurt them more. And hurting blue reviewer doesn't make much sense because they're anyways like much higher than we in the ranking, and we won't overcome them anyways. And yeah, this is kind of maybe a bit hand wavy, but I guess the intuition that I try to demonstrate in this example is that to be successful, a strategic reviewer needs to choose the ranking depending on how their own quality compares to the quality of others. And importantly, compared to rating setup in which the dominant strategy was to give 0 to everyone, irrespective of how our quality compares to the quality of people or submissions we need to rank. And this is a key difference between two setups. But this difference, we can actually employ it. Because think about truthful reviewers. When truthful reviewers need to rank others, they of course don't consider their own quality because it doesn't matter for them. Like you need to only rank 3 people. And if you are truthful, you just consider how they compare to each other, but you never think about yourself. And in some sense, the rankings output by a strategic reviewer are dependent on their own quality, on the quality of their own submissions. And the ranking output by truthful reviewers are independent of their own quality or the quality of their submissions. And we see there is already a difference between behavior of strategic and truthful reviewers. And this is the difference we can actually test for. And this is in fact the main idea of our test, which I now introduce, but I won't go into too many details. So the main thing, I guess, to understand that to test for strategic behavior, we uncover some difference in behavior of strategic and non-strategic agents. And then we employ some statistical machinery to actually test for this in the real data. So we'll come to real data soon, but let me introduce the test for completeness. So how does the test work? For each reviewer, we find the final evaluation of their own under given reviews. So we take reviews from all people and find the evaluation of this reviewer, final evaluation of this reviewer. Now we compare this quantity to the final evaluation of this reviewer if they gave a random ranking of other reviewers. So if I am the reviewer, then I have some people to rank, and we compare my position under actual reviews versus my expected position if I were given random reviews. Now for truthful reviewers, this quantity kind of may be sometimes positive, sometimes negative, because they don't choose this true ranking in any way. However, a strategic reviewer can always choose their rankings they output such that it helps them as compared to the random ranking. So for the strategic reviewer, we can expect this quantity to be positive. And for non-strategic reviewer, this quantity is kind of maybe positive, maybe negative, but there is no bias. And what the test does, it just sums these quantities across all reviewers and declares the presence of strategic behavior in the system if this quantity is larger than some threshold. So this threshold is determined via careful determined via permutation test. And I definitely won't go into details, but we can show that by doing so, we design a test which is first reasonable. Like we expect this test to detect strategic behavior. And we can also prove that when there is no strategic behavior, our test is unlikely to raise an alarm. So if there is no strategic behavior, then our test can control, the false alarm rate at any requested level. Yeah, and again, like if it is fine if you didn't get all the details of the test, it's not so important. More important is the intuition. But see that now we know that we don't detect the strategic behavior when there is no strategic behavior. But what happens in real life? Like, what if there is strategic behavior? Is our test able to detect it? And to answer this question, let me continue to the experiment. So to evaluate the detection power of our test, we ran an experiment. And in this experiment, 55 participants were peer reviewing each other's hypothetical performance. So how the experiment was set up? A participant comes to the system and they play a game in which there are 20 people, and each of them needs to review the performance of 4 of others. So if say we as a player, then the system tells us that, hey, our performance is 7, and we also given a performance of 4 other competitors. And what we need to do, we need to rank these competitors to ensure that our position is improved. So essentially, these 55 participants, they played the game, and each of them was instructed to manipulate. So we actually tell them, hey, go and manipulate to improve your position. So why did we do this? We did this to learn what strategies people use when they need to manipulate, because otherwise we kind of don't know what is the right manipulation strategy, and we want to elicit it from people. So we recruit people, ask them to cheat, and collect data. So additionally, there is one more detail. So in the first 4 rounds, we instructed everyone that they play against truthful competitors. So we told them, hey, there are 20 people. You're the only one who manipulates. So please manipulate under this assumption. And in the last round, we told everyone, hey, now there are 20 people and everyone may be engaged in manipulations. So think, what would you change in this case, like if everyone is manipulating? And then, yeah, we were given some feedback after each round, but this is not important. So here, before I go to the results, let me make some remark. So I designed this experiment, and the first idea was to test it on Amazon Mechanical Turk. So I wanted to collect data from Turkers, and I set up the task and went to the platform and get some data. And what I observed that people on Amazon and Turk just don't want to manipulate. So even though I ask them and even offer some bonus for some creative manipulations, what they tell me is that, hey, I still don't believe that you will not reject me if I won't be truthful. So I don't want to be, to be strategic. I don't want to cheat. I want to be truthful. So if you tell me, that value of some performer is 18, and another value is 3, then I don't want to, swap them, and I want to be truthful. So I tried it several times. We're giving kind of significant bonuses to people, but they were still, many of them were still reluctant to manipulate, and they were saying, okay, I don't need your bonuses. I better be truthful. Even though you tell them that, hey, this is just a game, this is just a research, and it's not like true life, they still don't want to engage in manipulations. So to overcome this, we went to students, and we asked like 55 students to play in this game. And let me quickly outline what strategies we learned from people. So in the first 4 rounds, people were playing against truthful competitors. And in the beginning of the game, many of players were using the reverse strategy. So we discussed the reverse before, and we've seen that it is not, it's not the right strategy to use, but still many people started from the strategy. However, like our feedback about the quality of manipulation kind of lets them quickly realize that this strategy is not the right thing to do. So closer to the end of the game, we observed an interesting strategy that we call distance. And what this strategy tells you is to rank others, to rank your colleagues by distance from your value. So let me just give you an example. So assume that our true performance has 10 points. And we need to rank 4 of our colleagues who have different values of performance. So the ground truth ranking is that like orange is better than blue, better than green, better than brown. And the distance strategy tells us to find our closest competitor, so the performer whose performance is close to our, and put it at the last place of the ranking. So in this case, a blue guy who has like the value 12 is the closest to us because we have value 10. So we take them and put them at the last place of our ranking. Then we find the second closest competitor, which is green in this case, and put them at the second last place of the ranking. And we continue until everyone gets ranked. So the idea of this strategy is to find the closest competitor, so one who either can overcome you or who you have some chances to overcome, and put them at the last place, and then proceed until everyone is ranked. So there were some other strategies which people use, but I'm not, they're kind of esoteric, so I'm not going to discuss them. This is the strategy that most people converged to as the game progressed to round 4. Now let's think about round 5. In round 5, it is much more difficult to manipulate because you don't know what others are doing. So in the first 4 rounds, you kind of knew, hey, there are 20 people, I can manipulate, others are guaranteed to be truthful, so I can find a good strategy that helps against truthful people. But now you know that everybody manipulates, so you have much less information about others, and it's much harder for you to find the strategy. And what it resulted to was that many people were kind of, clueless about what to do. So they said, okay, I will perform as I was performing the previous round. So they kind of say that, hey, others will do different things, and this will somehow end up being close to truthful. So I will pretend that everyone else is truthful and use the same strategy. However, what is interesting is that some people managed to predict this behavior. So some students said, hey, I think many people will still use distance even in the last round. So I shall design a strategy that works against distance. So they designed a good strategy that is a best response to the case when all others play distance. And we call the strategy 2x distance. So I'm not going to talk about it now, but this is just an interesting observation that some people manage to predict how others behave and adjust their behavior to it. Okay, so this is the experiment. So we collected this data and we had like a data set of strategies that people use. And in total, we have like about 7, I think, different strategies. So now we can evaluate our test against these strategies. And this kind of lets us to see how a test behaves in practice. And here are the results. So let's look at so first of all, yeah, again, I try to not to go into details, but our tests kind of have 2 regimes. In the first regime, we have additional evaluations from reviewers who have no interest. And this can be like manager who rank their subordinates, or some external evaluations. So our test can take these evaluations and improve its power. And on the right side, we see the behavior of our test when there is no additional reviewer. So when we have to work on purely observational data. And as we see, and how the images are built. So for each round of the game, we take strategies that people used in that round and create synthetic agents who use these strategies. We then supplement the set of these agents with truthful bots and vary the fraction of truthful reviewers in their synthetic simulations. So as we see, when there are many manipulating reviewers, so when a fraction of truthful reviewers is 0, our test has a non-trivial power, especially when it has additional reviewers. So as number of fractional reviewers, a fraction of truthful reviewers increases, our test of course loses power, which is reasonable. And at the end, when there are no manipulating reviewers, our test goes beyond the significance level. So it kind of detects it doesn't detect the strategic behavior very often. So what we can see from here, that our test has a non-trivial power, which is especially good when we have additional rankings from reviewers who have no interest in the game. And additionally, our test can control for the false alarm probability. So that's it about their strategic behavior. And to sum up, so what we did in this work, so instead of designing a system to prevent strategic behavior, in this work, we designed a test that detects the significant presence of strategic behavior in the system. And this test can be used, to identify strategic behavior on real data. And this test can inform system designers on whether they need to take some actions to fight strategic behavior, or it is fine, to go as is because folks in your system are not engaged in manipulations anyways. And yeah, that's it for the first part. So I'm going to the second part, but yeah, if there are some questions, I guess it's a good time to ask.
I have a question. Well, when you showed your experiment, you told that you invited people to participate in this game and to submit responses, and then you evaluated their responses using your test and using the ground truth data you have. My question is, doesn't it is it possible to run maybe a simulation or a computational experiment in which you randomize your responses and you see maybe some randomly obtained solutions that allow you to reveal some manipulation patterns?
Oh, you mean kind of randomly simulate answers and then see if some of them are helpful or not, and use those which are helpful to gain some insights into what are the right strategies.
Yeah, that's the idea.
Yeah, that's I guess a reasonable suggestion. I mean, I guess kind of here's the problem here is that when you see there are many moving parts, because the success of the ranking depends in fact on the assignment, on how there is a complex assignment, right? There are a bunch of agents who evaluate each other's, and there is an assignment of agent to agent, right? So one to many. And the success of manipulation in any particular case depends on this assignment. But this is what you don't actually observe. Like agents in the system don't observe the assignment, right? They don't know it, so they can only kind of play against expectation. And that is what you cannot really model in simulations, because this assignment is kind of very high dimensional. So I'm not sure, like, if I see that this ranking is helpful against this assignment, how it helps yeah, I think it will be just hard to generalize.
Okay, cool. Thank you.
And in principle, like, what is the best strategy, right, is to just run. You can, it's not, if you have to rank 3 people, right, then you can just look at all possible rankings of 3 and compute your expected position under randomness in the assignment. And this is like computationally optimal manipulation. And we can just, code it and find it. But I think that people don't do it in their minds. So what is interesting about this experiment is, like, we just see how people think about when they don't have full information. So there are like some hidden factors like assignment, but they still, work around it and find some nice strategies to work with. And actually, yeah, I told you about like 3 strategies, but there were others which are kind of maybe not always helpful, but at least you see how people were thinking, and it's pretty nice to see.
Okay, cool. Any more questions? I see a question in the chat. Let me read it out loud. So the question is it true that participants were given true scores of others? What if participants were uncertain to some degree about the scores of other participants?
Oh, yeah, that's a very good question. And yes, so in the experiment, participants were given the true scores of others. But then after we learned strategies, we were simulating. And in these simulations, we were, adding various levels of noise to evaluate how our test, to evaluate the robustness of our test against noise. And so, yeah, in the true experiment, there were true scores given to people. But then in evaluation, we were varying the level of noise to see how our test behaves. Yeah, but this is a nice observation. At least I have someone who follows the talk very carefully.
You received the comment, thanks. So which means everything's fine. Thank you.
Yeah, so yeah, if there are no more questions, then let's move on to the second part. And I guess we may need to skip the third part, which is good, because yeah, the second part, I guess, is also interesting, and this is about noise. So what do I mean by noise here? Is it mistakes that people make when they need to do some tasks? And I guess this is something I don't really need to motivate. All of us are humans, and we all make mistakes sometimes. But the question is how to account for them. So we know that people are noisy and make mistakes. So what do we do about them? And yeah, let's talk about it in the context of crowdsourcing. So you submit your task to a crowdsourcing platform, and people there may be like, they may not have enough skills to solve your task, or they just may be inaccurate or, distracted. So they can make mistakes. And the golden rule of crowdsourcing is to assign each task to multiple performers, and then aggregate responses of these performers into a high accuracy answer to your task. And in fact, there has been a lot of work on aggregation, and there are like a whole zoo of methods that take data from crowdsourcing workers and then aggregate it to boost the quality of data overall. So it starts from a simple majority vote. So if you have a task and bunch of responses, you can just take the most popular, and yeah, this will help you already. But then there are many more, many very sophisticated methods that improve beyond majority vote. But I think what is kind of overlooked in the crowdsourcing literature is the assignment. So how do we, can we assign workers to the tasks such that, it also helps us to improve the quality? So we know how to aggregate, but typically on crowdsourcing platforms, assignment is not really controlled. So how it happens in practice, so you come to a crowdsourcing platform, you put up your task, and then anyone can take it unless you put some filters. So you can filter out some performers, but still it appears in the list of everyone, and people can just take it. And typically what is important is how much you pay for the task, how much time it takes. So you get very diverse people to solve your task. And as I said, like I am not aware of like principled implementations of any assignment strategies on the platforms, but I guess it's kind of important. And let's see how other applications go about it. So the problem of noise arises not only in crowdsourcing, it's also in peer review and everywhere else. And many in this, maybe we can learn something from these applications and then translate it back to crowdsourcing. And for this, let's look at academic peer review and specifically at conference peer review. So how academic conferences proceed. Each time they have a submission deadline, and then by this deadline, like thousands of papers may be submitted to the conference. And there is also like thousands of reviewers who are willing to review the papers. And the question that arises: how do we distribute papers to reviewers? And yeah, let's see how it is done in peer review. And the key component of the assignment is similarity. So for each pair of a paper and the reviewer, a number that measures expected quality of reviewer in reviewing this paper is defined. And the higher the similarity, we can assume that this indicates the higher competence of a reviewer in reviewing a paper. So how are these numbers defined? Yeah, I won't go into details, but typically we have a paper and each reviewer has a profile of publications. So how we can compute the similarity? We can just compute a lexical similarity between the paper and the profile of a reviewer. And this is in fact what is done. And there are a bunch of approaches to this, but the high level idea is to look at the paper and the papers authored by reviewers. And also typically reviewers are asked to indicate their competency in reviewing some papers. So there is a specific stage in which each reviewer sees all the papers submitted to the conference, and they can tell the organizers, hey, I like this paper, or I don't like that. I mean, not like, but I am able to review this paper, and I'm not qualified to review that paper, and so on. So all combined, we have a number which measures the expected quality of received review. And of course, for each paper, we it's reasonable that we want each paper to be assigned to competent reviewers. So we can define a quality of the assignment with respect to a specific paper as some similarity of reviewers who are assigned to this paper. So now that done, the key question is how to choose the assignment. What is the right criteria for the assignment? And let's start from the conventional approach. So a conventional algorithm finds an assignment that maximizes the total quality of the assignment. Yeah, and this is a constraint optimization problem because each reviewer cannot review like more than 6 papers, and each paper must be assigned to 3 reviewers. So subject to these constraints, we find the assignment that maximizes the total quality of paper reviewer pairs in this assignment. And this algorithm is like extremely popular, and it was employed by NeurIPS, ICML, AAAI, and many other conferences. But what in kind of our recent project, what we observe about this algorithm, that first it may be unfair to some submissions. And what I mean by fairness here, or unfairness here, is that if you maximize for the total quality of the assignment, then you can assign all relevant reviewers to one paper and all irrelevant reviewers to other paper. And to show you an example, so consider just 2 papers A and B, and consider 2 situations. In first case, we assign paper A to very weak reviewers, so the total sum similarity is 0, and we assign paper B to strong reviewers, total similarity is 1. In contrast, in the second case, we assign both papers to kind of reviewer of medium quality. And if you look at this, the second case seems to be more fair, because in the first case, like paper A just doesn't get anything and paper B gets everything, which is somewhat unfair. And it's more fair. It's better to distribute reviewers more equally. But as you can guess from the objective, this algorithm would prefer, the second option is better, but this algorithm would prefer the first option. So this algorithm would assign paper A to weak reviewers and paper B to strong reviewers. So in this sense, this algorithm is unfair. And second, it doesn't have any guarantees, like any theoretical guarantees on the overall objective of the process. So in the conference, our goal is like to identify good papers for acceptance. And while this algorithm seems reasonable, in fact, it doesn't really have any guarantees on how well it helps us in identifying best papers. So in one of my recent projects, we designed an alternative algorithm. And we did this by simply changing the objective. So what this algorithm does, it finds the assignment such that the minimum quality is maximized. So the paper that gets weakest reviewers should get as good reviewers as possible according to our objective. And this objective is a little bit harder to optimize than the first one. And we need to design some approximations. But in fact, we designed an algorithm which is by default, by design fair, because in this way, we cannot really assign some paper to weak reviewers without good reason, because we are forced to find good reviewers for all papers. And secondly, we show that this algorithm is also statistically optimal for recovery of top papers under a popular model of noise in peer review. So I'm not going to talk about this algorithm in detail. This is like kind of very detailed and nuanced, but let's see how they compare to each other. And this algorithm will compare it in a bunch of setups, and eventually they will compare it on the confidence data in ICML 2020. And what we observed, and what is a good feature of our new algorithm, that in terms of fairness, so in terms of objective of our algorithm, we of course gain a lot as compared to the conventional algorithm. So like improvement is about 20% and sometimes even more. But what is really surprising is that in terms of the conventional objective, in terms of the objective of the total quality, we don't lose much. And this is kind of a win-win situation, because we design a new algorithm that performs very well in the conventional objective, but also performs much better in the another very reasonable objective, because fairness is like, of course, very important for peer review. And this algorithm was implemented in ICML 2020, which is, I think, kind of good, because there were many reviewers, many papers, and yeah, we, I think, managed to make the process more fair this year. But yeah, you see that in peer review, a lot of research is done on how to assign papers to reviewers and how to assign them carefully. And you see how nuanced the analysis is. So we don't really compare like random to something. We compare like one good algorithm to another good algorithm. So let's now see if we can do something similar in crowdsourcing. And now I'm going to tell you about one experiment I ran there. And yeah, I should really like warn you that this is just a toy experiment and just a demonstration. So don't take it like, don't put too much value on it. But let's see if we can take intuitions from peer review and just simply apply them to crowdsourcing without much changes. So instead of reviewers, we now have workers on their Amazon Mechanical Turk, and instead of papers, we have a task. And what is a task in my experiment? So the task was to simple classification. So people had to, identify the country whose flag is shown in the image. And what is the key component of the assignment? The key component are similarities, and these similarities are somehow missing on crowdsourcing platforms, because we don't know like a priori how well a person in solving a task. So to kind of define similarities, we did the following. So we put up 6 projects, and in each project, we were asking people to identify countries for flags, using countries from some regions. So in the first project, there were countries from North and South America. In the second project, there were countries from Western Asia, and so on. So we had 6 projects, and within each project, we had like 10 countries, and we split these countries in 2 sets. So one set is evaluation, another is test set. So what we do, we force people to solve everything. So everyone had to identify countries of all 60 flags. And then what we do, for each region, we use the evaluation set to define similarity of a worker to countries in the test set. So here, look at the example. We have a worker, and we have their answers on the evaluation set for America. So they took, like, say, 4 countries correctly. And this means that their similarity with the remaining 2 countries in the test set is 0.5, because they took 4 out of 8 correctly. So we define their similarity with the remaining countries to be 0.5. And we do this with each worker and with each region, and eventually we get similarity metrics. And now what we do, we think if we can do better than random assignment. So kind of on crowdsourcing platforms, the assignment is in some sense random, because we don't do any. The baseline thing is we don't do anything to filter out performers, and whoever takes the project does the work. So in some sense, the assignment is random, and in some first iteration. And what we do, we compare the random assignment with conventional assignment algorithm and the fair assignment algorithm, which I discussed in the peer review example. And the results are that first, both conventional and fair algorithms gain a lot as compared to random algorithm. And in fact, the error fraction is decreased by 4 times. So the accuracy grows significantly. And second, we also observe some difference between conventional and fair. And we see that fair algorithm leads to a little better accuracy. And yeah, this is also an observation. So I should warn you that here I can't really tell you about statistical significance because we only had like 80 workers and 60 questions, and we were bootstrapping. So for these values are averaged over a bunch of iterations, and for each iteration we were bootstrapping, or not bootstrapping, but randomly dividing countries into test and train sets within each project. But still, yeah, and yeah, so I don't don't put too much value on this example, but still kind of intuitively it shows you that there is a lot in crowdsourcing that can be gained by the assignment. Maybe you will not really improve your accuracy 4 times because here our estimates of similarity were kind of a little bit tricky. Like in real life, you cannot ask people, I mean, maybe you can, maybe you cannot. This is an interesting question to think about of how can we implement, this assignment in crowdsourcing. But it seems to be that there is some juice in this because yeah, you can, in this two example, at least you gain a lot from doing some kind of simple assignment and simple strategy of defining similarities. And maybe like, the platforms, they have a huge amount of data about performance. So maybe they can predict, say, the accuracy of a performer on a project or use some statistical models. I mean, I think it's an open problem and I hope that it will be solved sometime soon. But at least to me, it seems that there is some value in this. And Dima, do you have a question?
Yeah, question. Could you please elaborate on this for a little bit? I'm curious, is it correct that you have somehow obtained the metrics of similarities between the annotators, and then you used this metrics to evaluate the quality of assignment, right?
Oh, I use this metrics to evaluate the quality, like the right and the two right columns are about the quality of the assignment, but accuracy is like I knew their answers to the questions. So I was just computing 2 assignments or 3 assignments using different algorithms. And then I just take majority vote over corresponding answers and define accuracy in this way.
Yeah,
so how I do it, like I first obtain the full matrix of answers. So each of the 80 performers answers all 60 questions. And then I use these answers to subsample them according to assignment. So,
I'm just curious about the notion of similarity in this sense. So you treat a pair of annotators similar if they showed similar performance on evaluation set, but when you but can you instead learn or infer these similarities from their behavioral data or something like this? So can you, is it necessarily be based on control tasks, or you can use other kinds of similarity to gather these insights?
Yeah, I mean, this is, I guess, a very good question. So how I define similarities here, a little bit like unfair, right? Because I first see how people behave, and then I kind of, this is like a definitely good way to define similarities. But on platforms, when workers come, they didn't start any project, so you don't know, you cannot use this method. But yeah, I mean, I myself didn't have any access to data. Like, I mean, I myself didn't have any access to historical data about performers. But I think and I hope that in practice you can gain a lot, from learning it. Because on platforms, like, for example, some image labeling task, you see how this person did it like in the past, and this is some estimate of the similarity. But still, even this approach maybe somewhat useful. People can hypothesizing now, it can be the case that there are a bunch of projects and each of them put some small evaluation set online, and the worker comes, solves small evaluation sets of 10 projects, and then this gives us a measure of similarity, and then we do the assignment. So say we have like 10 projects, 1,000 performers, we ask them to solve the small evaluation tasks, and then we match them. In this way, we kind of going to offline set. I mean, there are a bunch of caveats, right? That on platforms we need to do it kind of online, and we can't really force people to work on anything. They have to agree on it, so we can only maybe recommend or push them towards it, or maybe we can force. I don't know. I think it's a very interesting problem to work on, and I myself work more like on peer review, and here I kind of just show this example to maybe spark some interest into the problem, because I feel like essentially nothing was done on it. At least no like serious attempt was done on organizing matching and crowdsourcing. And yeah, I guess even like minor results will be very valuable to start off. So I guess maybe if someone is looking for a research problem to work on, then this can be a nice problems to think about.
Maybe I may ask. Think about this one more time. So when it comes to the assignment, so usually crowdsourcing platforms assign at random. So first come, first served. And in this case, how can you actually provide good assignment if you, unlike in the research conference scenario, when you have this, the complete set of reviewers at the same time, in crowdsourcing, you have a stream of people who join the platform to take some task and do it. So how can you filter out the ones who will be better or worse? Well, cool. I think.
Yeah, I mean, I guess again, a crude solution, right, is to look at this. If your stream is like intense enough, you can take a batch of the streams, or like wait for say 30 seconds, see for people who are coming to watch for the assignment, and tell them, hey, we are computing something for you. I mean, yeah, again, ignore this for now, but you take a batch, and on this batch you do that. This is one example. But yeah, I'm sure that online recommendations are actually like everywhere, right?
That's right. Okay, thank you very much, and let's continue.
Yeah, I mean, I guess I'm kind of running out of time, and this is good because for the bias, maybe I will not go into details, but let me just demonstrate you one thing, which is like so blatant that I can't even believe it. So this is a true story from the journal called PLOS ONE. So there, a paper was submitted, authored by 2 females, and this paper received a review, which says like that it would probably be beneficial to find some male researchers to work with. So this was a real complaint of a reviewer about the paper. And the complaint was that, hey, this paper is authored by female researchers, and the reviewer probably couldn't believe that that women can write papers. I don't know what was going on in the head of this reviewer, but this is just a blatant demonstration of sexism in peer review. And I think this is a horrible example, but at least in this case, we know that there is a sexism and there is a bias. But in real life, the bias is much more subtle, so you can rarely see it obviously, like in strategic behavior. And what I do in my research, I just design tests, to uncover very subtle biases in human decisions. But yeah, we're running out of time, so I'm just skipping. I didn't have much, but I'm skipping this now. And let me just quickly summarize. So in this talk, yeah, we didn't discuss biases, but we discussed strategic behavior and noise. And yeah, I also work on biases, but in principle, there are a bunch of problems with people which arise in their decisions and arise in many applications. And these problems can propagate to to data you collect, and then to many, it can propagate much further. And these issues may have far-reaching consequences on careers, like peer review. If your paper don't get accepted, it may hurt you a lot. And this problems with human judgment can have far-reaching consequences and even multiplied, because in crowdsourcing, we collect some data, we train some algorithms, and the issues on data propagate to our machine learning models. So there are a bunch of issues, and it's very important, to understand how to detect them, how to fight them, and how to design, the systems in principled manner. And I think this is an ongoing, direction of research. So yeah, if again anyone is looking for research problems, then I highly advise you to think about these kind of issues. And yeah, I'll stop here. And yeah, if some questions are here, I'm happy to answer.
Questions, please. I mean, I'm really wondered about that screenshot from the PLOS ONE journal. It's like, well, it's quite weird in my opinion. But when it comes to the statistical test, that you showed in the first part of your talk, how did you evaluate it against the, how did you study its theoretical properties, or how does it handle things, and maybe some extreme cases?
So yeah, theoretically, I studied how it behaves when there is no bias, when there is no strategic behavior. Like, because it's very important, when there is no strategic behavior, you shouldn't claim it. So you shouldn't make false alarms or type 1 errors. So this part is very rigorously studied, and we show that yes, our test, like we clearly identify the assumptions which you need to make to ensure that type 1 error is controlled properly. And then for the power, like for the ability of the test to detect strategic behavior when it is present, here I don't have much theoretical analysis, and mostly because it's kind of not easy to to theoretically show that some strategies are good. Like, because with ranking it's kind of tricky to find them. But we instead of theoretical analysis, we just run it on real data and evaluate power like on kind of semi-real data. So here too, we kind of have both types of analysis that complement each other.
Thanks. More questions, please? Okay, I have actually a lot of questions about everything. I think we can discuss it later. And if there are no more questions, I think we can say that's it. And thank you very much. Oh, no, sorry. There is one question. Oh, it was a thank you message.
Yeah, thank you everyone for
it was a great talk. I really enjoyed it, and I hope all the attendees enjoyed it too. Thank you very much, and have a nice evening.
Thank you.